And I did a Hubble Fellowship there, and then I went to Yale University for a postdoc, and now I've been here for about 4 years on the faculty at LSU. Go Tigers. Okay. This is the first talk I've given in a long time. I'm actually kind of nervous. It's weird. Wait, should I share my screen now? It says it'll stop your sharing.
Yeah, go ahead. The floor is yours. And if you need me to help, just let me know. Yeah, we're happy to have you here today.
Okay, confirm that you can see what I want you to see right now.
Yep.
Yay. Okay. So silly me, I sent in a title of the talk. I didn't use the title for this talk, but it is still on the same topic. The original topic, Planet Hunters and the most mysterious star in the galaxy. And I will talk about both of those. But this is my title slide, and what it says is, where's the flux? And here, flux in astronomy terms means brightness. And this is a logo that we made up to describe a couple of things about this very interesting source that we found. And that's what I'm going to tell you a story about tonight. But, you know, largely you have this logo, which is, you know, shaped like a human eye. And this is how this object was actually discovered. So it was discovered by average people looking through data from a NASA space telescope and picking out signals. And the signal that they found was what you see in the pupil of the eye here, is these very strange variations in the star's light output. And this logo also symbolizes our call to action of what we want to do to learn more about this thing, is we want to watch it and we want to see what happens. So I'm going to tell you a story about it and then give you updates, and that's where the whole now bank thing is there, just to, you know, pull everybody kind of up to date on this very fun project that is kind of like a career-long project at this point for me. Okay, so to get started, come on, PowerPoint. Yay. Okay, as promised, Planet Hunters. So Planet Hunters is a citizen science platform. It's part of the Zooniverse collaboration. A lot of people have heard of Galaxy Zoo. We can go in and just use the human brain's amazing ability for pattern recognition to pick out patterns in data, things that are kind of difficult for computers to pick out, but quite easy for the human eye to pick out. And we developed the Planet Hunters mission specifically to look for look in time series data to search for planets. And how that was done is, originally it was using data from the Kepler Space Telescope. And this telescope had an extremely boring job of just staring at this one tiny piece of sky continuously for 4 years and taking a data point of over 200,000 stars in that field every 30 minutes. That's all it did, is it monitored the brightness of 200,000 stars. And what it was looking for was a chance alignment of one of these stars hosting a planet, and this planet periodically coming in front of, between you and the star, and blocking out a tiny bit of light. Here you see this little cartoon over here. You see the star's normal brightness. And as the planet goes in front of the star, it kind of dips down and makes that little U-shaped drop right there. And so that was Kepler's main purpose. We put all this data into the Planet Hunters website, and we had folks search for planetary signals there. And I was part of the science team, just collecting the observations, follow-up observations, and writing up these results. It ends up that this graph shows discoveries made by planners, and they're outlined in red, and the discoveries made by Kepler, meaning that the NASA Kepler team, they had an automated pipeline to go through and search for these planetary signals. What's shown here is an orbital period. So this is in a logarithmic scale. So you have 1, 10, 100, 1,000, and you have planet radius, and this is in terms of Jupiter radii. So I have the position of Earth right here and the position of Jupiter right here to kind of give you a sense of what kind of planets we're looking at here. And I just wanted to note that, you know, of these, dozens and dozens of planets that Planet Hunters have found, they've also found and recovered a lot of the Kepler planets, but it's kind of meaningless to show it on this plot. These are just the ones that got missed in these automated pipelines that we're able to discover with the help of volunteers through the Citizen Science Project. And so to me, this is pretty interesting because here you have, they're largely long period signals. So kind of, with orbits in between, say, Venus and Jupiter. And these are pretty interesting area of parameter space, if you ask me, if you're, looking for life and that sort of thing. So it worked, and that was fun. And the way this story goes is, we have users that are looking for planets, and but you look at every star, and stars do lots of weird things. And our users came across this one star, KIC 8462852, and they started chatting about it because it was a little weird. So I'm going to zoom in on the first feature that they found. This feature right here. Here you have the star's brightness and a drop like this, much like the cartoon that I showed you before, where you had this drop in light. But there was a couple of things that were different that our users were commenting on the chat box. The first one is that this shape right here was asymmetric. I mean, it has this kind of very strange slope over here on the left-hand side. And that would indicate that whatever is going in front of the star here would not be circular like a planet. They also noted that the duration of this event right here was really long. So if you have a planet going in front of a star, you have a duration of a couple of hours or so where the planet blocks that star's light. Here you have something that lasts for over a week when it's transiting in front of the star. So this is very, very strange. They started chatting about it. It got put on a watch list of, okay, well, when the next set of data comes out, what are we going to see? And so there were a couple of other events that were pretty small, but about 2 years into the mission, we come up upon this very large event right here. And so a planetary transit in front of a star is typically around 1%. Sometimes it could be less than that. This right here, this event right here went down 15%. So it blocked 15% of the star's light, which is extraordinary. No kind of planet can do that. This event also lasted for about a week, and it is also very asymmetric. So it slowly dropped in brightness down to 15%, and then it went back straight up again to normal. So again, the Kepler Space Telescope, it observed for 4 years. This is the entire 4 years that it observed this one star. And I'm going to zoom into the last part here because this is the truly insane part of looking at data for this star and really just trying to figure out what is going on. Stars just don't do this sort of thing. So what we see here, not single dips or anything like that. We see multiple dips of multiple shapes, durations. There's ups and downs within the dips, almost like, there's events kind of superimposed on top of each other. And this whole thing lasts for about 90 days or so. And then the Kepler mission ends. And this one very large drop in brightness is over 20%. So this is bigger than something 1,000 times the area of our own Earth. So it's quite extraordinary. And this got the volunteers really excited, and they came to us, the science team, and they say, hey, what's this? And of course we're planet hunters, and we say, hey, that's not a planet. But a little bit more chatting about it did seem quite interesting. And so the first thing that you do as an astronomer is you go and you learn about the star itself and see if you can find any clues to what's going on. And so astronomers have what we call an HR, Hertzsprung-Russell diagram. And this just basically shows how hot the star is on the bottom axis right here, and how bright the star is on your y-axis right here. So most stars fall on this kind of diagonal called the main sequence. Here you have our sun, right? Stars evolve up this way. You have supergiants, and then you have these are kind of dead stars over here. Anyway, so our sun is right here, and the star in question, KIC 8462852, is right here. Just showing you this to put it in perspective of all the things out there, right? This thing is kind of similar to our sun. It's about 50% larger in mass and radius. It's about 4 times brighter, but overall, it is pretty normal star. Looking at it in a little more detail, we don't see anything really peculiar about it either. So there's no signs of youth. There's nothing weird in its spectrum, nothing like that. And so what could be happening? Well, there's several different views that you can take, also called families of solution. And so here I have a couple of different scenarios that I'm going to illustrate for you real quick. First, you have us on Earth and you see the star. Perhaps something weird is going on with the star itself. Another scenario, you could have something going around the star. Third scenario is there could be something going between you and the star, so kind of an interstellar space. And lastly, you could have something going on with your telescope. Maybe there's like monsters or bugs or something in it. I don't know. But that is also a possibility. So what could be causing this? Of all of these, astronomers typically lean to the second one here. So there's something going around the star. And so of these scenarios, we thought of quite a bunch. There was a large laundry list of these things. So here you have a protoplanetary disk. And so this is essentially a very, very young star that is formed from a giant collapsing cloud of dust. And you have the star in the center and the swirling bits of material around it are what eventually will form planets. Perhaps these clumps were kind of rotating in and out of view and making weird signals in our data. There's another idea, it could be an asteroid belt around this star. So, a much more mature system, but having this asteroid belt aligned in our line of sight, perhaps this could make the observations that we're seeing. There's also an idea of a ringed planet. This is, would be something quite extraordinary, like Saturn, but like Saturn on crack, I guess you could say. It would have to be very, very large, but it's possible. We know of some systems out there with rings. And lastly, there could, be some sort of catastrophic collision that had happened within this solar system, much like the Earth-Moon forming event, where you have a Mars-sized object smashing into proto-Earth and making the moon out of it. And there's a whole bunch of debris that falls off. Well, the issue with this is if you have a star and you put stuff around it, it actually messes up the light output that you detect with your telescope. So for instance, if you look at this top panel right here, you have a star, right? And this is its energy output with the color of light. So this is brightness, color of light here. Normal star, but if you put something around it, say like a dust disk or something like that, the starlight is going to leave the star and then it's going to hit the material in the disk and heat that material up. And you're going to have this signature of what we call an infrared excess. And depending on the shape and location and everything of the material in your disk, you can have this signal shown in several different ways. And so we do not see this with this star. That was one of the most peculiar things about it, is that you can suggest a lot of scenarios to explain what is happening if you put stuff around the star, but we do not see in the infrared, we do not see any brightening over here. And so the way around it is you still have something around the star, but in our solar system, we would call them comets. This object would be in an elliptical or like egg-shaped orbit. So essentially, when the object goes around closer to the star right here, that's when it would get big and outgas, right? And it doesn't spend that much time here. It kind of zips along and the sun slingshots it back out, and it spends most of its time way out here in the depths of the solar system. And so you wouldn't have an infrared excess except for when you would have the object very, very close to the sun itself. And so this seemed like a plausible explanation, although it was pretty far-fetched. It was the best one that we had, was invoking some kind of exocomets. And here is a picture of the press release that we sent out of a very, very giant swarm of comets headed towards the star. And so we wrote a paper about that. And here you go. There's the title, Where's the Flux? And that's WTF. There were other things that we said about it that also say, that also had the initials WTF, but I'll leave that up to your imagination. Anyway, so the fun thing about this was that this actually got some press in the sense that, ooh, there might be comets around another star. And that's pretty exciting because comets in our own solar system, when they come zipping around our sun, they leave debris in their way. And then Earth, when it goes around in its orbit around the sun and it flies through this debris, you would get meteor showers. That's where meteor showers come from. And so what if you have like a ginormous swarm of comets and you're around this, star up here, then you would get like a really crazy meteor shower show. One of the catches here is the models that have come out to try and recreate the light core, the data that we saw from Kepler of the star, shows that it would take hundreds, if not thousands of comets, very, very giant comets, to go between us and the star to reproduce what we're seeing in the data. And this is quite extraordinary, to say the least, because that's not just, that's the minimum number of comets, because you still have comets that would probably go above and below you and you wouldn't see them. And so for this reason, we actually wrote a proposal to look at the star in a different way. And news of that proposal leaked in this article right here. And it created quite a fuss. Because we wanted to actually look at the star and see if there was some sort of extraterrestrial civilization, any kind of signal from that sort of thing. And yeah, so that kind of went viral, completely unexpected. We actually didn't get the telescope time. We did in the end. But anyway, on this, okay. So first I wanted to say, extraordinary claims require extraordinary evidence. And the second thing that I wanted to remind you guys is that with 3 parameters, I can fit an elephant. That means that, if you start allowing pretty much any kind of thing in your imagination into your model, like you can recreate the data, anything that you want. And so here is an example I have here of something that is non-symmetric going in front of this star right here. And you can see the date down here will kind of tell you like what's going on, right? Here's something non-symmetric, and see how you see you're not getting that clean U-shaped dipped, but you're getting something kind of funny shaped. Okay, so thank you, Joe, come on. There we go. So the catch with this is it doesn't quite explain everything. Even with your many parameter model, is you have to deal with what we call waste heat when you're talking about advanced extraterrestrial civilization. And so here I have a picture of a house. This is invisible light, it's what our eyes can detect. And you can companies to come out and take data on your house and see where you don't have very good insulation. And so they come out with these infrared cameras, right? And they take the same picture of your same house, and they'll show, here you have it in red, where you have a lot of heat leaks in your house. And that way you can put better insulation, windows, or stuff around your doors or things like that. So imagine that you have a very advanced civilization. They're going to be putting out a lot of this waste heat, right? It's the same idea. If you're using your phone a lot, it's going to heat up. So if you're using a lot of energy, it's going to heat up, and you're going to be able to detect that. And again, we did not see this heat in the infrared, much like, for the astrophysical scenarios as well. And so this is a problem, but then again, here you have, you're invoking aliens. You can explain things by, so what if they just covered everything up and they have the back door open, and that's where the heat is all escaping. Just a fun aside, I did get to go alien hunting. It was quite awesome using this Green Bank telescope, which is the largest steerable telescope in the world. And we pointed at Mars, and we actually detected a really interesting signal. This is actually Martians communicating with us at Earth, and we intercepted that signal. So you recall, we do have rovers and satellites going around Mars, and so this is just an interception of their communication. But hey, it proved that things worked. Anyway, so there you go. There's the signal right there that we saw when we looked at Mars. Okay, so that's kind of the background of where things were. But then, the world was kind of watching, and we're kind of waiting for a break, some kind of clue to what's going on. But then things got a little weirder. Imagine that. So here you have a fellow from actually, Brad Schaefer. He's an expert in this archival data called the Harvard Plate Stacks. And he actually took a trip up to Boston and looked at data for this star that goes back to 1890. And what he saw is these blue points here. You can see a couple of different fits on these lines. Basically, these lines are sloped downwards. So this is saying that over the past 100 years, the star has dimmed. It's gotten dimmer by about 20%. Now, this in itself is extraordinary. Stars don't do that. And if you're invoking comets to explain your observations for the features we saw in the Kepler data, Occam's razor says that you must also invoke comets to explain this dimming as well. And that's, on the order of, 500,000 or so to 1 million comets perfectly orchestrated to come in front of the star and block out the light as we're seeing it today. So that's a bit tough, kind of threw a wrench in our theories so far, even though they were kind of bad theories to have it. But the community wasn't very receptive to these results. Don't want to get too far into it, but it was quite controversial. A lot of folks were saying that you couldn't pull these kind of signals out of an old data set like this. So my friends Josh and Ben, they were like, hey, we can settle this by looking at data from the Kepler Space Telescope, not their data that they search for planets, but their calibration frames. And this is what they found. They found in the 4 years that Kepler observed this star, here you have the, time is equal to 0. You see a slight slope down, a very sharp drop down, and then a continuing slight slope again. This drop right here, that's on the order of 3% in 4 years. And here you can see in gray, that's the, ooh. Here's that big cluster of dips that we saw at the end. Here's that one in the middle. This is quite extraordinary, right? And they went and did all sorts of kinds of tests to, figure out, one, is this real? Is it a detector thing? Is it just like, that is something stars do? We just never knew about it. And this is what they came up with. If you're familiar with statistics at all, basically, if you look at this entire light curve for the star, the probability of anything being like that is it's around 8 sigma different than the whole bunch of things they looked at in different ways. So yes, it is quite extraordinary. So that got weird, right? We have this long-term dimming, and then we have these crazy dips, and we really want to know more about it. And really the only way we can do it is to pretty much get observations of when this star is doing its thing, when the stuff is in front of the star. That way we can study it really well. But if you look at this 4 years of data that we have here to go from, the duty cycle, or the occurrence of when these dips come, right? This kind of few and far between, right? You can't really predict either when the next one is going to come. And so that presented us quite a big problem. But there was a tool that, meaning a actual observatory that addresses this sort of things, time domain astronomy. And I like their old logo, which was "We keep you in the dark." Now it's something different, and it's longer, but I use this one. I think it's much more descriptive. Basically, they have a network of telescopes dispersed in different latitudes across the globe, and you have, longitudes, and then you have a southern network, and then you have a northern network. So basically, as the world turns, the sun comes up in Tenerife, it is getting, it's already dark in Texas and out in Hawaii. And so you can have continual watch on something pretty much all the time. The issue with getting observations with this thing here is it's a private telescope network. And so we got inventive and kick-started this Kickstar observations. So again, kind of calling back to the community for help. If folks had a couple of dollars they were willing to spare and they're interested in what's going on, they could help, support this project. And we're able to raise enough money to get some telescope time and just kind of sit on the star and wait and see what happened. And that's what we did for a very long time. It was still very exciting, but also very nerve-wracking. This is an example of, how bright the star is in a 100-day period, and nothing's really happening. But then one day in May, we started to sense a drop down in this star's brightness. And that was really, really exciting. We were able to contact a bunch of other astronomers and trigger more intense observations with a whole bunch of different instruments and track this pretty much for the next 8 months. And this is essentially what we got in the end. So here we have what's known now as the LC family of dips. We have LC, Celeste, Scarbray, and Anchor. I call this Watt because it comes right afterwards. It kind of comes up a little bit. And then you have Caral Soup and Evangeline. The names for these have stories, but I didn't really like the naming them, the day 1512 dip. I think it's much more personal to give it a name, much like the asteroid people, they named them too. So we named these and it made it much more fun. It kind of gave folks a little bit of ownership on, because folks would vote on the names and things like that for these dips. Anyway, we wrote a paper on this, and you can see there's a lot more people on this paper than the last one, because there was a lot of overwhelming response to the call that we put out for more observations. And I want to summarize what came out of that. First one is, this is not, any artifact or bug on your telescope from the Kepler Space Telescope, because hey, we found it from the ground. We just found it with one telescope. We found it with a whole bunch of telescopes. So yay, it wasn't, it wasn't fake. The second thing was, there's no clear pattern. Here we have the 4 years of Kepler data plus, these dips that, lasted nearly a year, and we don't see any pattern here. The only thing that we could maybe pick out as a pattern is this shape of Skara Brae here, this solid black line, that is the Kepler data, and these dots, that is the ground-based data from the Las Cumbres telescope. And they kind of look the same. I don't know. Anyway, there's no clear pattern. Next thing that came out, we got a bunch of really nice spectra from this star. We had spectra from when nothing was happening, and we had spectrum from when whatever stuff it was going in front of the star. We looked at the difference between those, the prior versus during, and there was absolutely nothing interesting happening there. There was also no radial velocity or Doppler variation. So there was no very close in gravitationally strong object that was, yanking it around in its or if it was in orbit, it would be gravitationally pulling it around, and you could see it in the spectra, and we did not see that. Another really cool thing that happened, we got the WISE Space Telescope. It's out there hunting for asteroids. It's up there in space, and it's a survey telescope. It points at all areas of the sky. And then here we have observations of this star. It happened to be looking at it about 2 weeks before the LC family of dips occurred. But the cool thing is that WISE, every now and again, it wants to point somewhere else randomly because it wants to avoid where the moon is. And so at this time, this random time, it pointed at this star during the LC dips. And this just totally by chance, it pointed to this star right here. And so we're able to get infrared observations before and during, and we don't see any changes here. So there's no bright heat from the infrared material that we can detect. This is polarization data. It basically says, okay, well, there's nothing weird in the space around the star. I'm not going to go into that much because there's a lot more cool things to look at. Okay, so this is the money plot right here. This is exciting. I'm going to take a minute to unpack it for you. So the bullet points here says ELSI is chromatic. So what that means is that when we're looking at the star, unlike the Kepler Space Telescope, Kepler only had one color of light it was looking at. When we designed this project looking at it with ground-based telescopes, we could look at it with different colors, what we call filters. And so here you have blue, we have kind of like a yellowish, and we have a reddish kind of light, right? These observations taken during the ELSI dip, you can see that they have very different response, like how far down they go with respect to each other. The blue dips down a whole lot more than in the red. This is what it means by being chromatic. So if you have, imagine a planet going in front of a star, it would block the blue light and the red light equally. It's just an opaque object. It's going to block it all equally. But if you put a dusty something in front of a star, it's going to give you a signal like this. And so depending on how deep down the difference is between these colors, you can actually get informed on the grain size and the composition of what is going in front of your object. So that's super fun. Okay, another thing that came out was this long-term dimming was investigated again, excuse me, and this time over several different colors ranging from the UV down to the infrared. And what we see here was pretty much the same as what we saw over here, is that the slope of this line in the blue was much, much greater than the slope of the line over here in the red. And so this also indicates that it's not any sort of, completely opaque object. It's, some sort of dusty business. This was shown again, and I'd like to show this separately, because this was a project that was conceived on Astro Hack Day. It was conceived on GitHub, and people were like, hey, let's look at these observations and see what we find. And there you go. Here you have the Kepler curve. Remember, I showed you the 4 years of that kind of drop by like 3% in those 4 years. Here you have an ultraviolet brightness point right here, and then one right here. It's clearly dropping more in the blue than the Kepler observations did in the red. So that's kind of fun. Another thing that resurfaced, which was something new that we've seen so far, is that, hey, we have an archive of 12 years of data. Here we see, where's my mouse? This red data right here, this is the Kepler observations, right? And these black and then blue points right here, these are ground-based observations. And just overall, if you look at this 12-year duration, we only saw this going down point, right? But there is a point right here and possibly right here where the brightness is actually going up. So before, we've only seen the brightness going down, but this shows that there's actually periods of brightening as well, which makes things a little bit more interesting. Okay, so what happens next? That was in 2017. We had the ELSI family of dips. We made this really stupid prediction in our original paper. We said, hey, these Kepler dips, right? The two big ones, this one right here and this cluster right here, they were separated by about 750 days. So if we wait 750 days, well, nobody looked at it because we didn't know about it then. 750 days after that, that was the ELSI family of dips. That's pretty exciting. So what would happen based 750 days after that? That would be the fall of 2019. And some other work came out as well saying, hey, we expect there's to be some, 1,500 day periodicity in this. And, they actually ended up lining up around the same time. So we were expecting something, maybe expecting something in 2019, but the star does nothing that we expect it to. Still, we actually got very lucky in that the TESS Space Telescope, which is much like Kepler, is kind of point and stare, was observing this star at that time. And so what I'm showing here is just kind of the amount of time it looks at the portion of sky. So Kepler stared at a single bit of the sky for about 4 years. This mission stares at a single bit of sky for about 27 days, and then it moves on. There's a chance that you'll get overlapping points, and that's what you see up here in these other colors. And we were lucky enough to get observed in two what they call sectors side by side. So we got two 27-day chunks of data. And when the data came out for this star, the TESS guest observer's office, they actually made some tutorials and things with this star as a test subject, showing people how to, work with the data. And you have something like this, which is very not impressive at all. There's really nothing going on. I guess folks kind of forgot about it when Sector 15 came out, because I was fiddling around with it and I'm like, wait a minute, I see something here. I don't think I'm doing this right, because I think I would have heard from them having, made the examples from this. And so I replied to Geared and I was like, hey, I'm getting something like this. And here, it's very faint, I apologize. Here you have the star's brightness. You have a blip right here. And then you have a bigger blip right there. This is very, very exciting and very new. And it seems like, the mission office, they said, well, hey, that is real. And here is a close up of it down here. It's binned. And this actually looks not like anything else we've seen before. It actually looks very planetary. You see how it's very symmetric and clean. And this one lasts for only about a day, which is also kind of unique for this star. And so if we look at everything in our ground-based monitoring, this is what we have. From back in the early 2016, we have the Elsie family here, not much happening here. And then over here, we have a couple of very small features, but we observed it with a space telescope. So that's pretty cool. This is a close-up. The different colors of the data points just indicate the different Las Cumbres Observatory stations. So green is Texas, red is Hawaii, and this is Tenerife, blue. Yes. So here you have not much happening, and here you have in Sector 15. And you can kind of see, I'm going to show a close-up here in a minute, that there are some points that drop down at this point. And so our ground-based monitoring actually did successfully pick up something of this size and duration, which is quite remarkable. It's reassuring, at least. Anyway, so this is a close-up, as I promised, of what we saw here. And we're pretty proud of the fact that the plan that we have is robust enough to detect dips from the ground at about 1.5%. Of course, from space you can do a lot better. And this dip itself is unlike anything else we've seen before. It's symmetric. It lasts about a day, and it's about 1.5% deep. This one over here is just a couple of tenths of a percent deep. And so lastly, I want to comment on this. This is the same test data here you see at the top. Where is my mouse? There. And in the colored points here are now showing the different filters. So we're using the blue filter and the red filter here, like we did in the Elsie data. And recall how when we observed the Elsie drop in light, the blue dropped down a whole lot more than the red. And that seemed to indicate there was some sort of dusty material in the way. Well, this shows not that. So again, it's something very, very different. We have these two data points, they're dropped around the same amount during this amount of time. And so right now I am working with Madison LeBlanc, her picture's right here. She's an undergraduate at LSU, And we're working on modeling these as they were planetary transits. Gosh, it's like freaking black belt stuff, man. She's fearless. I'm very proud of what she's doing. But yeah, we're still trying to learn what's going on here, and see if we can get any, glean any more information about, the orbit itself, and also the kind of material that it could be there. So this is no color, as opposed to the LC dips that were chromatic. There is an arrow. Okay. So in summary, this thing is probably not aliens. Okay, that's the last resort hypothesis. Our current understanding is that it's likely due to dust, but just generally speaking, it's some sort of magical dust, because the data that we have in hand points to dust, but we haven't been creative enough to develop a model to put dust around a star that doesn't give off any infrared signature. So remember, if you put stuff around a star, it's going to start glowing in the infrared, and we still don't see that. And so things that we want to do in the future, we just want to get more data. Basically, we want to characterize everything in all wavelengths and higher cadence, everything like that. And we want to model everything. And as I alluded to before, the circumstellar, or when you have material around a star, that scenario is preferred with astronomers. But there are some folks in the other camps, such as, there's stellar variability. So maybe there's star spots of some sort. That's not completely ruled out. And so, exploring these properties or ideas as well is something that, we also want to do. And so with that, I want to end it with a couple of links. Here is the Planet Hunters link right here, which is now not showing Kepler data anymore. It's actually showing data from the TESS Space Telescope. It's super fun. You take like a tutorial that takes less than a minute, and then you can go hunt for planets. And if you are, a first identifier of, a signal, and you get your name on a paper, and that's like super exciting. Anyway, come help join the fun and find planets. And I think this is the only star out there with its own subreddit, which is fairly active. It's not very active right now because we can't see the star. It's behind the sun. It will be active, I believe, in the next, back up again in the next couple of months. So yeah, that's it. Thank you very much for having me.
Hey, so thank you, Dr. Boyajian. I'm going to clap for everybody. If you could give a virtual applause of the reactions, you can give a clap to our speaker tonight. That was a fascinating talk. It reminded me, I'm actually a co-author on that paper that you published, and I have a lot of questions, but I want to give the audience a chance to ask questions. So if you have questions for our speaker, please post your questions in the chat. What we will be doing is taking questions for our speaker, and then at the conclusion of the Q&A, or depending on how things go, we're going to have a virtual tour of our observatory, starting and led by our observatory graduate students, starting in a little while. So I guess I will start with a question, and it's kind of so this star, just to make sure I understand what's going on, was unlike anything that had ever been seen before. No one had ever seen anything like this in all of the years of data that people had looked at in the night sky.
So that's a question to me?
Yes.
Okay, so we have seen signals like this from stars, right, in their light output, but it is associated with something that is very young, and so we know that they have debris disks around them, so they're glowing in the infrared. So like, one connects to the other. This one doesn't have that association. It is, very mature and old, and it doesn't have the infrared excess. And so something on this scale is never been seen before.
Okay, we got a question. I I have a theory about particles that do not produce much infrared light. Could it possibly be ice grains?
Ice cream?
Ice grains? Like dust made of icy particles?
Yeah, because sorry about talking, but like essentially, because like my reasoning with it is like it reflects most of the light that hits it, so you obviously still don't see the light, but at the same time you're not absorbing any light, that much light, so you're not going to heat it up that much.
Yeah, thank you for the question, Zachary. I'll turn it over to Tabby.
Right. So it's a very, very good question. We have it is still very open question also, what the source of this dust could be. So comets are basically like dirty snowballs that get near sun and they start outgassing and evaporating. The issue that we've found with the LC family of divs, these features last for a week, a couple of weeks plus. And if you put any kind of material, an icy material or dusty, any kind of material around a star like this, it's the solar or the sun's, the stars, the star's radiation pressure is going to blow all that business away in just a couple of days. So something has to be replenishing that source. And so with ice particles, you're going to have this stellar radiation coming to hit it, and there is going to be some sort of transformation of the how the material is existing. It's it's going to ice is a pretty volatile substance, and so it is, yeah, it's definitely an open question of what it could be and what could be replenishing whatever it is, to have these events last for that long itself. It's also something I didn't mention that is kind of like also mind-blowing a bit, is the amount of stuff that, imagine you would have a comet going in front of a star, like in the Kepler data, that very single feature in the middle. Say you have a comet going in front of the star, it's just one comet right at that point, and it starts outgassing and making a big cloud, and that's what's blocking the light. The problem with that is that if you have that much stuff around it, it's going to self-extinguish itself, meaning there's going to be so much dust and stuff around that comet from it outgassing that no more sunlight's going to be able to get in, and you won't have you won't have any activity anymore. So there's definitely a lot of open questions on what can host this.
Yeah, so I actually really appreciate this update because I had not known everything that's been going on since Elsie. I don't know if you remember, but so I think the reason I was on that paper is we happened to be at IRTF when Elsie was happening.
Mm-hmm.
And so we collected a spectrum with iShell, and I don't know if it was ever usable or not, or if you had a chance to look at it. But if you do someday, let me know offline. So Tess was able to observe it in, was it 1 or 2 sectors?
We got 2 sectors in 2019.
Okay. And after years of watching this with LCO, you saw the LC event, and then you saw this new event in Tess. Wow, that is just amazing. And then it looks like a planet this time, and not like not like Bizarro World of
it keeps throwing us curveballs. Like, I mean, that's why it's so silly of me to like try and predict things that are going to happen, because like you can't predict it. But still, it's like I said, a career-long project. It's fun. It's frustrating, but it's fun. It's like a love-hate relationship.
Yeah, so I mean that's amazing. And I guess is anyone monitoring this for Doppler velocities, or is it too hot of a star to do that? Do you know?
It's got pretty broad lines, but we have the APF. It's in the APF queue as part of the breakthrough. We threw it on their target list. We get a spectra here and there from Keck. It's not monitoring. And there are a few from it's not constant monitoring. That's my answer. It's something that's very hard to do when you just, want to monitor something like every once in a while. You can't just write a proposal for that. You're like, I just want one spectrum. Why would you write, 5 pages for that?
Yeah. Okay. Yeah. If you just need one spectrum, like once a year or something like that, that's.
Yeah. So
So
we
we
normally
still-
just bug people when things are happening.
Yeah. So we do. So we now know since the era of Kepler that at least some of the events, the source is when it dims in a chromatic way, right?
Right.
Okay.
Mhm.
But that's it.
Yeah, and there's no infrared excess at that time. The WISE
Yeah.
telescope has told us that. And the new feature in the test data that also got, caught by Las Cumbres shows that it's not chromatic.
So that test event was not chromatic, but the other events were.
Right. Mm-hmm.
Okay, then.
Yeah.
So my next question is this still remains the most mysterious star in the galaxy then. And I appreciate that you've been reserved about drawing possible interpretations, unlike certain professors at Harvard making the news lately. But I guess the question I have next is what's next? And in particular, as a professional astronomer, my question for you is related is two-part. Did you put in a proposal for the James Webb Space Telescope? And two, Kepler looked at 100 square degrees on the sky, about the size of 400 full moons. And TESS is looking at the entire sky, but with a much shorter time baseline. Are you looking for more of these types of stars in the test data? And has anybody seen anything? And is this Planet Hunters trying to do that now or what?
Yes. Let's see. Question. What's? Oh yes. So James Webb. Hell yes. We put in a proposal for that. Apparently, it's a very bright star, and so I don't know. My colleagues said they were optimistic about it. We will see because there are thousands of proposals that went in, and I'm sure they're all really great. I just really want to characterize, and it doesn't have to be during a dip, but we can rule a lot of things out by the sensitivity of James Webb in the infrared. And so there's that. The question is, have we seen anything like this in the test data? Is anybody looking? The answer to that is yes, folks are looking. Part of a proposal to look for, more dipper things like this in conjunction with young stars and also weird stars. So there's now been, I don't know if it directly came from this, but I definitely saw an uptick of using machine learning to classify light curves, and in particular, like pick out weird stuff, right? So you can have, things that are eclipses in one category and things that are flares, and they have all these different parameter space, and you find the ones that are weird, they don't kind of match anything. And, using this as, the kind of quintessential example, can you recover this, in a weird space of your results. And so those have, promising applications, I think. Of course, it's, this signal right here, showing it right here, this is, it sticks out like a sore thumb if you look at it with your eyes, right? And so if we had everybody looking at these light curves with their eyes, and we'd be able to see it pretty quickly. If it weren't for Planet Hunters, this would still probably be sitting in the data set. It probably just weren't be looking, hard to find like this serendipitous discovery. And something I didn't mention that does come up a lot, and it definitely came up a lot in the past, is that when when a astronomer looks at this data for the first time, they don't think it's real. When I looked at it for the first time, like, it's bad data, right? Everybody thinks that it's bad data, just flat out. And you have to spend a minute convincing them. And that's what our volunteers had to do to me at first. And that was a big hurdle. but it got checked out in all the different ways that we know about. And, you know, it's just like, what's the next weird one going to look like? Is it going to look like this, or is it going to look like something entirely different? I don't have the answer to that, but I think that using both citizen science and, you know, some kind of machine learning algorithm, it's promising to find, you know, the next weird thing. And along with that, you mentioned how Kepler looked at a small part of the sky, but it's still the size of 400 full moons. This is like, I mean, it's about the size of your fist if you hold it out in front of you, that portion of the sky. That's like less than 0.1% of the sky. There's a lot of variable stars that we know of that aren't in the Kepler field, right? There's no Cepheids in the Kepler field. There's no Arctur-Bohr stars in the Kepler field. They're like, and we know thousands of these across the sky. And so the fact that we get this one in the Kepler field, you know, does that mean that something like this is very common? Or does it mean that, you know, it's just by chance we have this one in the Kepler field? If it's something that's really common, it's going to have a not extravagant, you know, explanation to, it's going to have to be a physical process that happens all the time. So that's going to make it really hard if we have two. But it's also easier if we have two to study, because then you have two, and that's, you know, that's a lot easier. So that's a different way to look at it.
So we have a lot of, another unusual thing tonight is we have a lot of Zachs on the call tonight. Hello, Zach and Zach. So a question from another Zach. Would it be possible that a dust cloud at extreme range, Kuiper Belt or further, could explain the lack of detectable IR shift? So I guess maybe this stuff is so far out, it's so cold, so you're not seeing anything, but you just happen to have the right inclination that passes in front of the star. What do you think about that?
Well, well, there's a couple of different things that I skipped over. I wasn't sure about the level of the audience here, but so if we look at the Kepler,
level of the audience, just so you know, is everything from grade school through a tenured professor. So
okay, well, I didn't
audience.
want to. I aimed like for general. I didn't want to bore people or confuse them and make them mad. She was much better like that. Still entertaining. Okay, so if you look at the Kepler data itself, and in particular, like how sharp the drops are in the light curve, right? This is called a light curve gradient. So basically you have limits on where things are in an orbit based on a circular velocity. And the fastest thing that you can have gradient is if you have a nice edge. So say this is your star and this is, you know, nice edge going in front of the star. You imagine that the star's light can be blocked out at a certain rate as it goes in front of it. And then the velocity of whatever is passing in front of it changes as far as it's going out from the star. So we know from Kepler's laws, Kepler, the scientist, not the space telescope, is that the further away a planet is from the sun, or an object is from the sun, the slower it goes in its orbit. And so something out in the Kuiper Belt or something like that is going to be, its motions are going to be too slow, right, to produce that kind of gradient. There's, you know, of course, exceptions to a circular orbit. You can have an eccentric orbit, and that's where the whole, you can make a comet work come in, right? So you have, you know, your material, it's really far away from your star. Most of the time, you won't have an infrared excess because it's far away. You only have it when it's coming close in, and then you'll be able to get these gradients that you see as well. And so I might have these slides here somewhere if they're interested. I don't know how well that explained it. Did that work?
I thought you explained that, and Zach said, thanks, great explanation. So a question from Dr. Park, so I guess is also someone that has collaborated with you in the past, is probably not a new idea, but how likely is a test transit a progenitor object for all of the cometary material?
I don't know where that thing came from, but because we have 4 years of Kepler data, we don't see any signal like that. that is insanely frustrating because you would think if something is in orbit, it would, repeat periodically, even if it doesn't look like the same thing. So you would have some sort of periodicity in the Kepler orbit. There's been work done showing how the dynamics of a system would work if you have some sort of Jovian planet, say like Jupiter and its Galilean moons. Basically, there's some sort of close encounter with the Jupiter and its moons with the star itself, and it ejects the moons, which are icy bodies essentially. And so the moons are the ones that are kind of creating all the turmoil, but you do have that, the Jupiter that was left over in the system that would be kind of like, a parent body or something like that. There's also a paper that came out, it was a couple of weeks ago now, showing that this star does have a tiny, what we call an M dwarf or red dwarf companion to it. It's about 100 AU away, so it's pretty far. But that provides some sort of mechanism for gravitational instability of objects in the system, maybe at some point. When I looked into this a little bit more, objects like that don't really scatter things into the solar system, they scatter them away. But you have some sort of mechanism there that could make it work. And so that's another thing to look at. So.
Yeah, I was just thinking, you were talking about the fact that if this is in fact cometary material, it needs to be replenished in some way. Possibly the TESS object is what's replenishing that material. Essentially a giant Europa that's just constantly spewing out or outgassing material. Mm-hmm. So I didn't know if that was something that was being bandied around.
Yeah, I think we need to know more about that object that we saw in the test data first.
Yeah, that's crazy.
Our preliminary models are saying it's about the size of Jupiter, which is not Europa size.
Super Europa size, yeah.
Yeah, but you saw nothing for 4 years in Kepler like that.
Yeah, we saw nothing like that, and nothing periodic for so even if it was like the host or whatever, the main parent body, you would see something periodic as it would go around in its orbit.
If it's far enough out, you may just not have enough temporal baseline to see it.
So if that was the object that was creating the material that we saw in Kepler-like curve, though, then it would have to be associated with those clumps somehow at some point.
If you have material, sorry, I don't want to be huge, but I was thinking that you have a large icy body that is in the outer part of the solar system. It, for whatever reason, it's getting torn apart. That material then gets flung into the inner part of the solar system. And so you're seeing essentially this dumping of material from an outer solar system body into the inner part of the solar system. And you just haven't had a temporal long enough baseline in order to see this thing periodically orbiting.
Yeah, that's it's a very complicated picture. Like you have this long-term dimming and you have these dips, right? And you have to have, something that is, supplying the material for the dips that, would get blasted away in a couple of days for them to last for a couple of weeks. And so, my idea is that, yeah, you have a sort of family of comets. So there's some kind of close gravitational interaction that took the parent body, kind of stripped it apart, like the Shoemaker-Levy comet, right? As it flew into Jupiter, it kind of like pearls on a string as it fell into Jupiter's atmosphere. So something kind of like this, right? And as it goes around its orbit, it's kind of like grinding and pulverizing herself into smaller and smaller pieces. And, there are larger chunks that are, part of this. And so it's kind of smearing itself out in a torus. And then there are these larger chunks there, some which aren't being too big to be blown away from radiation pressure, some which are. But then again, that means you're putting a whole lot more material in front of the star too. So the whole idea of, the long-term dimming it really throws a wrench into any kind of thing that you can put around this star to explain any of the dips here. So yeah.
Well, I am convinced that this is awfully challenging problem to solve, and I wish you luck, Dr. Boyajian, in trying to solve it. So the last question, then we're going to turn it over to our observatory teaching assistants to give a tour of our observatory. And now I'm totally spacing on it. Well, why don't I turn things over? But I just want to thank you for joining us tonight. Let's do a virtual round of applause again for our speaker. And if I think of the question, if you're willing to stick around for a little while longer during the telescope tour, I will show you the, or I'll ask the question then. Okay?
Okay, I don't know if I'll be able to stick around,
Okay.
but thank you so much for having me. It was good to see you guys, and
yeah, likewise.
thank you all for coming and listening to this crazy story about this crazy thing.
Good luck with the follow-up. This is an amazing system.
Cool. All right.
Nice to see you, Tabby.
All right, Will and Kevin.
Okay, thank you, Peter, and thank you, Tabby, for your great talk. So as Peter said, we'll be doing the telescope tour part of the event now. So let me go ahead and share my screen. All right, and let me minimize some of this stuff. Okay, so what you're looking at right now is the computer, the desktop of the computer I'm currently connected to. So the great thing about the pandemic is that we can observe from home in the comfort of our own beds and apartments. And one of the things that makes that possible is that we have a set of cameras that give us a good view of the observatory so we can check in on how things are doing. So if I pull up those cameras, what we have here are three particular views. So in the top right, we have a control room where we would normally be operating the telescope. So we're currently connected to this computer towards the middle left here. And then in the bottom left, we have the an outside view of the telescope dome. So the telescope is in that building right there. Here's a door frame for scale, and that's about 6.5 feet tall. And unfortunately tonight we are going to be doing a closed dome tour, and the reason, at least part of the reason for that, is we do have a little bit of snow on the back of our dome right here. And we're kind of worried about what's going to happen if we open the shutter and then close the shutter, if that could get dragged somehow. So we're just going to try and play it safe tonight. So hopefully we can do an open dome tour on our next evening under the stars. And then, of course, in this view, we have our telescope. So we're just looking down the barrel of the telescope, and in the back, you can see the primary mirror. So that primary mirror is 32 inches in diameter. So what happens in this particular telescope is light is going to come in through this big opening right here, and it's going to bounce off the primary mirror and then shoot up to this weird contraption, which is actually a secondary mirror, which is about 1 foot in diameter. And then the light will reflect off of that and then down through a hole in the primary mirror, where it is yet again reflected by a third diagonal mirror into one of 4 portholes, where we have a variety of instruments mounted on the other side of the telescope. So a little bit about this telescope. It weighs, the optical tube itself, the telescope is about 1,000 pounds. The fork that you see it's currently mounted to is about 1,000 pounds, and then the base of the telescope is 1,000 pounds. One thing I always like to ask people is to take a guess at how much the telescope costs. And people always overestimate it. A common guess is $1 million, and I wish it was $1 million. But actually, the telescope here was about $300,000, and between 2018, 2019-ish, we put in about $150,000 worth of upgrades to the telescope. So that's a brief overview of our observatory and the telescope. So let me go ahead and actually move things a little bit just so you can see that we are indeed looking at a live view. So this is the software that we use to control the telescope. It's very easy, very convenient. So you can see that we have this yellow circle with a dot in the middle moving across the screen, and that is the telescope's position. So if we go over to the night owl cameras, we can see the telescope moving right along. And we can see some other stuff coming into view. Notably, we have a gear on towards the right, so that just moves the telescope up and down. And then we have a similar gear out of view towards the base of the telescope. That moves the telescope basically to the left and right. So we would usually spin the dome as well and move that around a little bit, but we have it positioned such that in the morning the sun is going to come up and it's going to melt this patch of snow on the dome, so I'm not going to touch that this time around. But anyways, we do have a couple of targets that we've picked out to show tonight. So these are targets that we have, or these are images we have taken with our own telescope. And I believe they were also processed. I believe Kevin will be showing you the colored images, so he can talk a little bit about how you get a colored image and what, you know, the raw output is of our telescope. So why don't I turn it over to Kevin, who can show you a couple of interesting objects.
All right. Thanks, William. The first thing we're going to be looking at today is the Orion Nebula. Now, the Orion Nebula, well, a nebula, I guess, is where I should start, is basically just a giant cloud of gas and dust out in space. This is one of the brightest nebula in the night sky. It's actually visible to the naked eye, and it's called the Orion Nebula because it's just south of the constellation Orion's belt. Well, the constellation is Orion, and the nebula can be found right south of the belt. It's one of the closest nebula, and it's measly 1,300 light years away, which is about 8 quadrillion miles, and it's about 24 light years across. So it's a huge, giant cloud of gas and dust in space. It's about 2,000 times the mass of our sun. And nebula are also sometimes referred to as stellar nurseries. They get this name because they're regions of star formation. These giant clouds condense into stars. And you can see in this image that I'm showing right now, these bright blue stars. And these bright blue stars are actually very young stars because this region, oh, thanks for zooming in. This region is known for stellar formation. Now, Will mentioned about the coloring of the images. It is true that these images were not originally in color when they were taken. Actually, I can go ahead and show you real quickly what an example of the image might look like.
Do we not have a black and white Orion? We should.
I don't think so, but we have a black and white image of the Whirlpool Galaxy, which is where we're going next. So I will show it then.
We can save it for then. Okay.
Sure. I guess we forgot to mention, but if you have any questions about the telescope or any of the objects we're looking at, I guess you can post them in the chat and we will answer them as we come to them. But I suppose we can go ahead and now move to our second object, the Whirlpool Galaxy. Gets its name obviously from that spiral structure that you can see very clearly, just like the Milky Way. And the Whirlpool Galaxy is a spiral galaxy with a smaller Seyfert galaxy interacting with it. It's this smaller thing, this smaller bright section you can see kind of hanging off of it. Seyfert Galaxy is an active galaxy, which means it has a supermassive black hole at its core that's actually accreting matter off of the main Whirlpool Galaxy. Now, the Whirlpool Galaxy, since it's a galaxy outside of our Milky Way, it is much, much further away at about 23 million light years from Earth, and it's about 75,000 light years in diameter. It's about 3/4 the size of our Milky Way. And I suppose I can now take this opportunity to show you an example of what we get directly from our campus telescope. Now you can see here our campus telescope, when we take an image with our CCD, it actually comes out in black and white. We're essentially just counting the number of photons that land on our detector and use that to create the brightnesses. We color an image by essentially assigning colors to different wavelengths. And while it's sometimes called like false color imaging, that's kind of a misnomer because we're not just making up colors, but we are assigning colors, and that's what we that's how we get the more visually pleasing images like this one. William, is there anything else to add about these?
As far as the Whirlpool Galaxy goes, no, not a whole lot, but just to add a little bit, so part of the coloring process is just taking a bunch of different black and white photos with different filters. So the camera we have has a variety of filters, so we can look at particular wavelengths of light. So we can get the blue light from an object, we can get the red light from an object, and we can get the green light from an object. And so if we have some photos that have red, blue, and green light, we can take those photos and use some image processing software and just kind of stack them on top of each other and then assign colors like Kevin said. And then we can, we'll have an output that's a colored image similar to what we have here. So that's the only thing I wanted to add. So thank you, Kevin. And the last object that we will show tonight is a globular cluster. So since Tabby was talking about a very special kind of star, I figured we should include something directly related to stars. So the last thing we're going to take a look at is so many windows, a globular cluster. So this globular cluster is M92 Messier 92. So it's about 200,000 solar masses and a staggering 11 billion years old. So for reference, the Earth is about 4.5 billion years old, and the universe itself is about 14 billion years old. So globular clusters are these really, really old objects. And they're typically the oldest objects in a galaxy, and they also aren't forming any new stars. So all of these stars are quite old. So we have a clear high density region of space that's being filled up by a lot of stars, especially as we get towards the center of the cluster. Things get really, really tight and compact. But what's the definition of a globular cluster? Well, it's basically just a collection of stars that are tightly bound by gravity. So globular clusters are typically found in what's called the halo of a galaxy. So a galaxy can roughly be divided into a disk component, which is where most of the matter is. It's where our sun is, our Earth is. So we are all in the disk of the galaxy, along with all the other, along with many of the other stars. But above the disk of the galaxy, we have a halo, and these globular clusters are often found in that halo. So typical distances between the stars in a globular cluster are on the order of 1 light year. For reference, the nearest star to us is about 4 light years. The nearest star is Alpha Centauri, for those who were curious about that. So, but that's just the average distance spaced across the entire cluster. If we just look at the center of the cluster, then the distances between stars are actually a lot tighter. They're on the order of separations similar to our solar system. So about the sun out to Neptune, which is a very small fraction of a light year. So these objects are just incredibly dense. And a question we can naturally ask is, how exactly do they form and how do they influence their surroundings? And this question is actually kind of easy to answer because we don't really know how. It's actually an active area of research. But one thing we can kind of say with reasonable confidence is that these globular clusters probably formed with or alongside their parent galaxy. They're probably not associated with a separate galaxy that might have been forming alongside the main galaxy. So that sums up globular clusters and this particular image. So that is the main things we wanted to show and talk about tonight. So like I said, we hope to have an open dome tour in the next Evening Under the Stars event. So in the meantime, if there are any questions about anything we've showed, we can answer that. Otherwise, I think that will be enough and we can wrap it up there.
All right, thank you, Will and Kevin, and thank you everyone for joining us tonight. We have a couple of questions, so I'll just ask them to Will. How to spell the name? I presumably Ritchie Creation is the, if you want to just call it an RC telescope for short, would that be okay, Will?
Yeah. So Ritchie Creation, yes. If I can type it into chat. Actually, no, I can't spell creation right. Never mind.
Neither can I. That's a tough one.
Yeah, if you Google it, Google will autocorrect it, probably. There's also a weird symbol over one of the characters.
Thank you, Kevin. And we have another question from Mariah Ahmed. What is the aperture of the telescope?
Oh, the aperture of the telescope is just 32 inches.
Great. Okay, I'd like to thank everyone for joining tonight. This will be posted to YouTube later, and we will have our next public evening under the stars in 2 weeks. Hopefully the weather will cooperate and we won't have snow on the dome this time, but I'm sure everyone got to enjoy, hopefully got to enjoy some of the snow over the past week. Until then, look out tonight. It's nice clear skies, so you can see the constellation Orion right now if you take a step outside, and we'll see you again in 2 weeks. Thanks for joining us.
Bye-bye.